So hello there, you are on Vectali and today we are going to solve the last set of 4 problems from mechanical properties of solids. Mechanical properties of solids is a very much easy chapter and the probability of asking it in JEE Advanced is quite less. And it was much difficult to find a good quality questions in this chapter. So we selected some of the best picks of it. Okay, for further solving you can refer other reference books 2 for this particular chapter. Let's go to question number 1. A steel plate and an aluminum plate, each of length L and width B, are welded on each other to make a composite plate. Okay. Thickness of the steel plate is Ts and that of aluminum plate is Ta. Young's moduli of steel and aluminum are Ys and Ya respectively. Find four force constants of the composite plate along X, Y, and Z axis. So first, this concept is much different, like it's an analogy between a spring and here they're speaking about a plate. Let's assume it as a rod which has a broad breadth compared to its length. That's the plate, right? So there's an analogy between that metal rod and spring. So how are we going to relate it? Just check this. Young's modulus is nothing but stress by strain, which is force, perpendicular force by area by delta x by L, where the delta x is extension and L is the initial length. If you rearrange these terms, you get this equation. Ya by L into delta x is F. Simple, right? So we have seen this somewhere. F is equal to Kx in case of springs. So if we apply force at one particular end of the rod, you get some extension. And this extension produces elastic force. So this is simply as simple as a spring, right? So the rod works like something like a spring with force constant Ya by L. That's it. That's the analogy. So here we are thinking the plate as a rod which has broader cross-sectional area compared to its side areas. Okay. Okay. Now the K is Ya by L. Now if you see here, what does this A represent? So if you take a particular rod, if this is a rod and this side it's A and here it's length L, that's it. So if we it's L is just similar to the length of um the length measured along the direction of application of force, right? And A is the area on which this force is applied. Simple, right? So let me just do along any of these axes. Let's say along x-axis, if we apply force, it's like, let me consider this as a one spring and this is another spring. These two are in parallel. So in parallel, I get K equivalent is K1 plus K2 and K1 is YSB. This is common. YS is common, right? Now, if we see here, what's the area? It's B into TS and B into TA. That's it, right? So that I have written here B into TS and B into TA by length L. So that's it. If you substitute it here, you get the K equivalent along x-axis. Similarly, I have done the same for y-axis and z-axis. Okay, let's go to question number 2. Stress strain curve of a metallic wire is linear up to the elastic limit with slope y. The wire is stretched gradually from zero load to a maximum stress sigma naught and then unloaded back to zero stress without any permanent deformation. Let the length of the wire be capital L and cross section area be A. Which of the following is or are correct? Maximum strain produced in the wire is, so this is simply direct. If you see Young's modulus is stress by strain. Okay. So they are asking the maximum strain. Maximum strain comes when we apply the maximum stress. Until Young's modulus obeys, right? If you see the graph, it's something like, it will go something like this. If you want me to explain this, I will just put it as a short video on explaining it. Young's modulus comes into the action till the proportional limit, right? So till the proportional limit, stress is and strain, the ratio is nothing but the Young's modulus. So stress by strain is Young's modulus. So maximum stress is obtained at maximum strain since it's a straight line. So simple. Maximum strain is nothing but maximum stress by Young's modulus. That's what the answer. So first option is correct. So let me mark it. So what next? Total elastic energy stored per unit volume at maximum stresses. So let's first derive this formula for total elastic energy. Simple. Same spring concept. In case of springs, we know that energy stored is half k into delta x whole square. So what about here? We know that k is ya by L, right? We saw it in the previous question. So just substitute it. Energy stored is nothing but half ya by L into delta x the whole square. So if you see delta L and L is there. So let's multiply and divide by L. So multiplied L is here and divided L is here. So half YAL into delta x by L the whole square. What's this, man? This is strain, right? So strain. And this is volume. So half into Y into stress strain square into volume. So if you replace Y with stress into strain into volume, it's okay with it. So that's it. The total elastic energy stored per unit volume at maximum stress is something this correct. Okay. So second option is also correct. The third, the total work done in loading the wire. So this is simple. If you see, mm, this is the total energy stored, right? So where does this energy come from? There is no change in some. Uh, there is a change in gravitational potential energy, but not for the wire, right? So total work done in loading the wire is nothing but the total energy stored, which is half into Young's modulus into strain square into volume. So that is sigma naught square AL by 2y. So third option is also right. What about the fourth option? The net work done in complete unloading and loading cycle is non-zero. This is a wrong statement because once you remove the load, when this particular wire is in elastic limit or the proportionality limit, it will come to the same state as before. So there is no loss of energy. So the net work done is supposed to be zero. So this is not the correct option. Let's go to the question number 3. So if you see here, a solid sphere of radius r made of soft material of bulk modulus k is surrounded by a liquid in a cylindrical container. When a mass m is placed on the surface of the piston to compress the liquid, the fractional decrement in the radius of the sphere that is dr by r is. Actually, they missed a particular detail. Okay, let's add it. So, based on what we know, the bulk modulus is nothing but the pressure whole divided by delta V by V, right? This is the bulk modulus. Now, what they are asking is dr by r in terms of radius. So, we can involve radius in volume. So, let's write first. V is nothing but 4 by 3 pi r cube and delta V is nothing but, if you differentiate it, this 3 comes here, 3 gets cancelled. So, 4 pi r square and dr. So, delta V is 4 pi r square into dr. Now this implies to delta V by V, which is 4 pi r square dr by 4 by 3 pi r cube. So I get 3 dr by r. There is another analogy for delta V. This is how, if you see, delta V is nothing but the small volume when the thickness of that particular shell, small volume of a spherical shell with thickness dr. So if you see the surface area of a sphere is 4 pi r square, right? So, and the thickness is dr. If you're just multiplying it with dr, the error exists, but when dr goes nearly to 0, the error also goes to 0. So that's why delta V is 4 pi r square dr. Now, if I substitute it here, I get case P by 3 dr by r. Now, the pressure in this case is mg by a, where, sorry, where a is the area of the piston. That is what the detail we missed. Case, if I substitute it directly, I get mg by 3ak. This is much simpler question. Okay, this is actually a PYQ in 2018, I guess. Now let's go for question number 4. A block of weight 100 Newton is suspended by a copper and steel wires of same cross-sectional area, which is 0.5 centimeter square and length root 3 meter and 1 meter respectively. Their other ends are fixed on a ceiling as shown in the figure. The angles subtended by copper and steel wires with ceiling are 30 degree and 60 degree respectively. If elongation in copper wire is delta LC and elongation in steel wire is delta LS, then the ratio of delta LC and delta LS is. So they have given the values of Young's modulus for copper and steel wires. Okay. And this is the particular arrangement. This is an JEE Advanced 2019 question. Okay, let's work on it. The first thing, simple. We can find TS and TC, basic NLM question. So if I do it with some procedures, right? In the horizontal direction, the component of TS and TC gets cancelled. So that's what yields this equation. TS is root 3 into TC over. And in vertical direction, I get TC cos 60 and TS cos 30 combinedly act in order to compensate this 100 Newton. So if I write, I get TC is 50 and TS is 50 root 3. Simple. Actually, if you see, this one thing is enough for the solution. Actually, we see these steps are much easier, right? So what our brain used to do is we will also complete these steps, but this is an unnecessary time wasting step. Now, generally, you write Young's modulus as here T by A because T is the force acting on that particular cable by delta L by L. So what they ask, delta LC and delta LS. So let me write it in explicit form. So delta L is nothing but TL by AY. Then if I take the ratios, this is what the thing I get. Here if you see, TC and TS ratio is what we need. We don't want the exact values. So our requirement ends here, right? And all the remaining terms are given by them. So we don't want to directly substitute those values. What people used to do is they will try to find out the value of many things and they will try to put the values here. That's making easy question into complex one. So if you see directly, the ratio is 2 for the Young's modulus, where ys by yc is 2. So this is 2. I can write it as 2. Tc by ts is nothing but 1 by root 3. And lc by ls, so root 3 by 1. If you directly write, it's 2. That's it. So we couldn't find much more difficult questions. Yeah, there are much more difficult questions in mechanical engineering, but in case of JEE scope, you don't get much more difficult questions. If you want much more difficult questions, just comment in this video. We will search for them and post it with the proper solution. Thank you for watching this video. Do subscribe our channel. Stay tuned.